Hello, so welcome to this lecture on basic math knowledge. I will basically talk about mathematical objects, operations and algorithms. That's, in my opinion, a good way of looking at mathematics, getting a little bit more familiar with some of the concepts. This is all very basic. It's the kind of stuff that's useful for students perhaps being interested in applying math to cryptography, applied cryptography and security. So we will also cover some very basic computational number theory. So we'll start now properly in terms of mathematical objects. So I want to talk about numbers, very simple numbers, and something else called polynomials, and finally booleans. So let's start with the learning objectives for mathematical objects. I want you to understand the definition of integers and how you can represent them using what we call the number system. We will then discuss polynomials in one variable, so you need to be familiar with the structure of what we call univariate polynomials with integer coefficients, and finally to appreciate the motivation behind introducing booleans. So let us introduce the integers and perhaps put them into context with some other types of numbers. Well, integers are really I would say, almost most natural mathematical objects, apart from the natural numbers. So the integers are the union of the positive and negative numbers. And we would include 0 as well. So for example, as you can see in this list, minus 333, minus 1, 0, 10, 2000, 10,000. These would all be integers. That's not too difficult. I'm sure you've all come across this. And the symbol we use in mathematics for the integers is the symbol Z, which basically stands for Zahlen in German, which means numbers. Now in a computer, it's quite straightforward to use integers and perform arithmetic with them, unless they're too big. If you have to deal with big numbers, and quite often in the applications, for example in cryptography, you have to deal with big numbers, then you need to be a little bit careful and you might have to implement your own algorithms or use some libraries. But anyway, the integers are a simple object, and then over time mathematicians have discovered that there are actually some other types of numbers which are also very important. And the sort of next level up from the integers are clearly the rational numbers. So you can think of fractions, all the things you can do with fractions. For example, you can divide. That's something which is more difficult with the integers. So apart from the rational numbers, you then also have the irrational numbers. So any number which is still a real number, but you can't actually write it as a fraction, is defined as being an irrational number. For example, square root of 2 is a good example of an irrational number. And finally, and that's well beyond the scope of this lecture, of course, mathematicians have introduced the complex numbers using the imaginary axis, but yeah, that's very unlikely to be actually relevant in the context of the security and cryptography in this series of lectures. So what's a number system? A number system is something we use in order to, let's say, encode a given value, an integer value, but it could also be a fraction actually, using digits. And traditionally, and you can probably guess why that is, the humans have used a system based on 10 different digits. And of course, you know the digits 0, 1, 2, and so on until 9. So these are the digits in the decimal number system. So why would this be typically for the humans? And if you think about it, then sometimes when we count, we use our fingers. So quite clearly, early humans were probably using the fingers to count and realizing that somehow this number 10 is a useful, value. And now using some formal terminology, we would express our given number d in terms of a number system with basis b. So here b could be any number, but typically for the decimal numbers b would be 10. So how would you write your number? You would write it as a sum of powers of b times the digits dk or di. So that probably looks quite complicated, but really it isn't. It's just that we're so used to doing it that we kind of lost the appreciation of this more generic expression. And typically if you put b equals 10, then you can clearly see that the digits, di, are chosen from the set of numbers between 0 and 10 minus 1, so simply the digit between 0 and 9. And the 10 these are the powers of 10. So clearly, for example, number 101 is the sum of 1 times 100, which is 10 to the power 2, plus 0 times 10 to the power 1, plus 1 times 10 to the power 0, which is 1. So in that way, you have expressed your number 101 as a sum of digits times powers of 10. So that's not really something new, but you might have not thought about it written in such a way. And then, of course, once you change the value for the basis, then it gets more difficult. So apart from the decimal system where the basis is 10, we also talk about binary numbers when b is 2, very often used for computers and logics. So here, what are the different digits that are available? The digits, remember, there are between 0 and b minus 1. So if b is 2, then you only have 2 digits, which is 0 and 1. Another system that's quite popular is the hexadecimal system, also used in computer science. So here, the basis is 16. So the different numbers, the different digits would be 0, 1, 2, etc. until 15. So you kind of wonder how would you express the digits. If they're greater than 9, well then we introduce as an abbreviation, we say A for 10, B for 11, until F for 15. I'm sure you've seen hexadecimal numbers written somewhere. Well, that's exactly what it is. It's an expression of an integer using the base 16 number system. And sometimes people also use the ternary number system, b equals 3, although that's a little bit less mainstream, but certainly it still deserves mentioning. And finally, you can also represent fractions. I did say this earlier already, by using a negative exponent in your powers of the basis. So for example, 1/10 is clearly 10 to the power minus 1. So 1/10 is nothing else than 0.1. So we introduce the comma or the full stop to then say anything further to the right of the full stop is actually a negative power, increasing negative powers or decreasing, depending how you see it. Okay, so that's in terms of introducing the theory, but it probably becomes clearer when you try to do the mini exercise. So can you convert, and that's not difficult at all, this binary number into decimal notation? So all you need to do here is to add up the powers of 2. Whenever there's a 1, you will take that power of 2 into account, and if it's a 0, then obviously you don't need to. So you add that up, you obtain your decimal number. As the next exercise, you do it the other way around based on a decimal number, 12. Well, it's very straightforward to express that as a decimal number. Can you also convert it to a binary and then perhaps to a ternary number? And then, slightly more difficult, we are dealing now with this number here, which is basically not, it has a full stop. So we're dealing here with negative powers, and the basis is 2. Can you convert this to decimal notation? So you get a decimal number. And finally, this fraction, 5/8, can you write this as a binary and perhaps as a ternary number? But anyway, the most important thing is that you can master the first 2 bullets, and that is maybe just to kind of deepen your understanding of the method, but it's less likely to be used in the cryptographic algorithms. So now I would like to introduce polynomials, and there is quite a lot of notation around the polynomials. And a polynomial itself is not actually a complicated thing. And you have been using polynomials at school quite likely without realizing that there were polynomials. Maybe you didn't call them like that. So a polynomial f, quite often we use the variables f, g, h for polynomials, can be written as a finite sum of powers of your variable times these factors, which are the coefficients. So you need to get used to this notation first of all. This funny thing here, the sigma, is basically a shortcut for denoting the sum. And then these are the coefficients, a index I, and I is like an index. It's like in a for loop. It's used to design the different coefficients, and this range of the index would go from 0 to d. So d here would be a positive number, and we call this the degree of the polynomial. And then this whole expression is called a univariate polynomial because there's only one variable, one type of variable. You could have more x, y, z, but we stick to just one variable with coefficients in the integers or over the integers, we say, and then you use this notation in mathematics. So here z means the domain of the coefficients, and we denote those, we use those square brackets to indicate that it is indeed a polynomial, and here it's just one variable x. Yeah, so basically when you have a polynomial given, you need to be able to match up those definitions, and you need to be able to tell, for example, for this polynomial 10x squared minus 5x plus 1, you need to be able to recognize the degree of that thing, and here I will tell you straight away. So the degree here obviously is 2 because it's the highest power in x. And what are the coefficients of this polynomial? Yeah, you would get a whole list of numbers. So basically the coefficient a2 in our notation, index 2, would be 10, a1 would be minus 5, and a0, which we also call the constant coefficient or the constant term, is plus 1. Because x to the power 0 is nothing else than 1 by definition, so there is no x here, it's x to the power 0. So that's the list of coefficients, and then we don't always actually write this thing here, the round brackets. Maybe I should just say f equals, that's absolutely fine, but I guess I was thinking of the fact that a polynomial could also be seen as a function, because later we will actually replace the value x with certain values, with integers, and that's nothing else than computing the values of a function, where f of, let's say f of 2 would then be another number, that's the output of the function. But you don't have to do this, just in case it helps, it makes it a bit clearer that we're dealing with a function here. And finally, I want to introduce the Booleans, and that's quite simple because these are, well, it's kind of a map between numbers and truth values. Truth values are false and true, which is used in logics when we are describing situations, conditions, implications, reasoning basically, which is a very, very important thing, of course. We can write down statements using certain operators, which I'm not going to detail now, but the outcome could be typically false or true. That's what we're interested in. And now you wonder, could we just actually use numbers for that? So we will say 0 corresponds to false and 1 to true. And that brings us a huge benefit, as we will see later, because we will be able to actually encode and almost sort of translate logical statements into numerical ones, which we can then evaluate mechanically, algorithmically, perhaps using computers. And also it will push us to think that the binary numbers that we use in our computers are kind of then, on the other hand, representing perhaps some truth values. And we could then interpret the values of the, remember, base 2 numbers, so the digits are 0 or 1, as truth values, but also we can compute with all this very efficiently due to the fact that computers are effectively just based on, no current or current flowing, and no current means 0, and current flowing is a 1. So we have a very interesting map between the logics and the truth values on the one hand, and on the other hand, simply the numbers 0 and 1. So let's just summarize then the content of this section. So hopefully by now you understood the definition of integers based on a specific number system. We've looked at mainly the decimal number system and then also the binary number system, and there are obviously other number systems around, but those might be the most important ones. And you should be able to convert between those different number systems. I have then introduced what polynomials in one variable with integer coefficients are, which is mainly a matter of getting used to the notations so that you can understand the structure of a given polynomial better. And finally, I have very briefly though introduced and perhaps motivated our Boolean values 0 and 1, and I've mentioned that that basically corresponds to truth values, which will become important in the future of this lecture. So having introduced our basic mathematical objects, we now would like to perform some operations on them. So I will explain how to perform operations with polynomials, working with polynomials, and then I will introduce something called the modulo operator. Now that is something which is a little bit less well known. It's quite specific to the use for cryptography and computer security, for the RSA algorithm, for example. And that's one of the reasons why we would like to do that. And that is then leading us to modular arithmetic, where we're going to combine the modular operator with the standard arithmetic of the integers, such as. So now in terms of learning objectives, we want to understand what modular arithmetic is. This is actually based on integers, on integer arithmetic, and the concept of the so-called modulo function, which I will introduce and explain. Then I want you to know how to work with polynomials. So based on the definition of a polynomial object as seen earlier, we want to perform arithmetic with it. And finally, the very basics of Boolean algebra, so also basically performing operations with truth values, the Booleans. So first of all, let me define what we mean by arithmetic with the integers. So we're once again dealing with our integers as basic math objects. And what we want to do now is we want to do stuff with them. We want to, for example, add them together. We want to perform subtraction. We might want to multiply them. And what we can also do is a special type of division. We call it the division with remainder. So the first two things are pretty straightforward, addition, subtraction, and I think multiplication doesn't really create problems either, but it is the division we might want to look at a little bit more in detail. So let's look at these examples. If you wanted to divide 10 by 5, then that's obviously 2, the quotient is 2. And then what you get is, that that's actually what we call an exact division, because clearly 10 is 2 times 5, there is no leftover, there's no remainder. So that's all straightforward. What do we do if that's not the case? What do you do if you actually want to divide 19 by 2? The problem is the output should remain an integer. So we can't just say, oh, the output is, 9.5. What you have to say is 19 divided by 2 is 9 with a remainder 1. So everything remains in the integers. That's exactly what we want to do in the division with remainder. One more example, 23 divided by 5. So here 20 divided by 5 is 4. That's as much as you can get in terms of the quotient. The result is 4, and then the remainder is 3. So what we say is that a number A is divisible by B if the division of A by B gives indeed a remainder 0, so if it is an exact division. So here the number 10 is divisible by 5. So now based on this definition of the division with remainder, we can introduce what we call the modulo operation. The modulo operation is something that people sometimes struggle to kind of get their head around, because maybe it's a little bit indirect, because in order to actually compute the output of the modulo function, you need to first do a division with remainder, and then take that remainder. So it's sort of 2 steps in your head. And that's what makes it a little bit more indirect. But with a little bit of practice, you should not have a problem with this. So let's look at these examples. 19 modulo 5 is 4. Why is that? Well, if you divide 19 by 5, then basically the quotient would be 3, because 3 times 5 is 15, and the leftover, so that's the difference between 19 and 15, is clearly 4. Hence we say that 19 modulo 5 equals 4. If you have a number and divide it by another number and the leftover is 0, so it's an exact division, then the output of the modulo operation is 0. So 10 mod 5 equals 0. Another example, if you take mod 2, then the output will always be either 0 or 1. In fact, more in general, the output of the modulo function is always at the most 1 less than the modulus. This is the modulus, right? We'll come back to this in a short while, but just for this example here, any number that is odd, such as 19, will clearly have the output 1 if you take it modulo 2. Last example, 23 mod 5, so 20 divided by 5 is 4, 4 times 5 is 20, so the leftover is the difference between 23 and 20, which is 3. That's reasonably straightforward. In case you wonder why on earth we want to introduce such a thing, well, actually, you have been using this for a long time in your lives when you look at the clock. Because actually, when we reason about the time, then we are doing a modulo operation, because there is a maximum number, number 24 in the 24-hour system would then turn into, let's say, if it's 25 o'clock, that's actually 1 o'clock, isn't it? So you always subtract the 24. So effectively, you are doing a modulo 24 operation. It's just that no one really talks like that. And as you might know, little children have problems in getting their head around the clock, and it takes them a while. It's again because of this nature of the modulo operation that reduces numbers from bigger numbers to smaller numbers. So that's basically maybe something you can use as a real world scenario to motivate the use of the modulo operation, and we will need it later for the cryptography and the algorithms. And then there's another problem with the modulo operation in terms of the notations, because over time in mathematics, several notations have effectively developed, and some of them are more used in the theoretical number theory, others are perhaps more used by computer scientists. And I just wanted to briefly talk about this in the hope that it would perhaps clarify things if you see them written in books or on the internet. So first of all, I would say there is a functional notation, and that might be particularly useful for you if you are a computer scientist or you're somehow used to having a function name written and you think of the input and the output of that function. So why not call the modular function here mod, and it takes as input the number a and then what we call the modulus. So if you want to compute a mod n, then why not just put them as input arguments to the mod function, and the output would be b. Unfortunately, that's not what you read in the math textbooks, but it might be useful for you to just remind yourself that the modular operation is basically a function with two input arguments and returning one output, one integer. So, for example, a mod n, where a is 15 and n is 4, so 15 mod 4, you would write mod 15, 4, and here the output is obviously 3. 15 mod 4 is 3, because 15 divided by 4 is 3, which is 12. Take the difference between 15 and 12, which is 3. There is another notation which I might refer to as the equational notation, and that is very much what the number theory mathematicians use, and it introduces a weird kind of equal sign, which is also called the congruent operator, the congruence, and it is a triple equal sign with 3 bars. And then what people write is they say A is congruent B in brackets modulo n. And what does that mean? It actually means a bit more than just computing the modulo function. It means that we're actually computing the modulo function for both the left hand and the right hand side. And then what we want is that those two values are the same. Although we're not actually writing down what that modulo value is, the output of the modulo function, we're just stating that they should be the same. And then the short form, to make matters even more perhaps confusing, is to just say A congruent B in brackets n. So you would still read it as A is congruent B modulo n, but what it means is that if you computed A mod n and write it down, then you compute B mod n and write it down as well, then those two numbers are the same. So for example, we can say that 15 is congruent 11 mod 4, because when you compute 15 mod 4, then that is 3. And if you compute 11 mod 4, that's 3 as well. So the modulo output is the same for both numbers. Another example, you can see that 4 is congruent 19 is congruent 24, so you can basically form a chain of congruence operators. Is congruent minus 1 mod 5, so here I'm kind of leaping ahead with introducing a negative input to the modulo operation. That is sometimes useful, but it's a bit more difficult to understand. So let's maybe for now not dwell on it, but let's just recap that here you can easily see that obviously 5 mod 4 is 4, clearly. 19 mod 5 is also 4. 24 mod 5 is also 4, which justifies the use of the congruence operator here. And we'll come back to the negative input later. So let's present some more properties and facts around the modular operation. So first of all, how can you compute this if the number's getting a bit bigger, if it's too tricky to do it in your head? Then you can use the Windows calculator, for example. It's got a tool to evaluate the mod function if you go to scientific mode, and also modern pocket calculators might be able to do it. And then I guess you can always try to use the internet, type it into Google, it might work. You can also use Wolfram Alpha, which is a very good website to perform math operations. So there are tools available to compute the modular operation, but then for small numbers, you're better off doing it by hand, because it also means that you're practicing it. And that should be useful. So there are some additional properties which help you with computing the output, and they're just useful in general. So first of all, we have already observed this, that actually a mod n, the output of the modulo operation with input a and n, will always be smaller than n. So why is that the case? Well, if you remember the definition of the mod function, the modulo operation, it is the remainder that you get when you divide a by n. And obviously the remainder will always be smaller than n. So that's clearly the case. Second property, apologies, that here should be if a is smaller than n, little typo. So if a is actually smaller than the modulus, then a mod n is simply a. Because then the division will be 0 and the remainder is simply a. That's a quick one. Then there's another property, and that's useful in the case of dealing with a negative input and trying to figure out what on earth the output of the modulo function is here. So what you can do is you can add any multiple k times, any multiple of n to your input without actually changing the value of the mod function. So here I've used the congruent operator. So what we're saying is, if you compute a mod n on this side here, and you compute a plus k times n mod n on the other side, then they're congruent mod n. In other words, the mod n value is the same. So imagine you have a negative number here, a, let's say -1, and you wanted to compute that mod 5, then all you have to do is you have to add a certain factor times 5. So basically add 5 once to see whether you obtain a positive number. Then you can compute it already. You know how to do it. So you would be done. So if a is -1, imagine you say -1 plus 5. So k would be 1. So -1 plus 5 is 4. Okay, so now this rule tells us that -1 mod 5, which is what you wanted to compute, right, originally, -1 mod 5 is the same as 4 mod 5. And now this rule tells you straight away, well, 4 mod 5 is obviously 4. So we have just worked out that -1 mod 5 is 4 mod 5. And if I'm not mistaken, then that was in the previous slide. Look here, -1 mod 5 is the same as 4. That's very useful. And the last property is kind of actually, it's this little statement, a little property, a little theorem almost, that saying that A is congruent B mod n is the same as the difference between A and B is a multiple of n. And that's actually, although it looks kind of obscure at first glance, this is actually the preferred definition, at least for a mathematician, of the modular operator, and it makes it much more easy to actually prove statements about the modulo operator, but perhaps less straightforward for someone who is just about learning about the modular operator. But I did want to put it down here because it might be used in proofs, for example. So for this second mini exercise, simply try to exercise the use of the modulo function by computing 17 mod 5, then a bit of a bigger number, 343, but a very small modulus. And remember, mod 2 is very simple. You can literally see this straight away. Then you need to reason, what might 0 mod 77 be? Think of the definition based on the division with remainder. Furthermore, 97 mod 98 is straightforward if you think of one of the properties. And then turn things around, 98 mod 97 should also be quite straightforward. And then the last example deals with a negative input. So remember that trick, how you can make that, that number bigger so that eventually you obtain the correct output, the positive output of the modulo 6 function or operator. So now we have enough concepts together that we can actually define modular arithmetic. So what is this? Well, it's simply still thinking about the integers and the different operations, addition, subtraction, multiplication. We would then add the modulo operation at the end. So what we're saying is we take some numbers, maybe we add them, we multiply them, but we always perform modulo n at the end and take that as the output of the modular operation. So we're turning the normal arithmetic into a modular arithmetic by computing modulo n at any stage, so that the output of our operations will stay in this range between 0 and n minus 1. Remember, due to the definition of the modulo operation, because we're taking the remainder effectively of the division by n. And then in terms of notations, what we say is we write simply a plus b mod n. So what this means is to take first the sum of a plus b, a and b, and then take that result modulo n. Same for the minus operator, for times, and then you can also use it for the exponentiation, so raised to a certain power, mod n. Some examples here. 7 plus 5. So 7 plus 5 is actually 12. And then, as you know, 12 mod 10 is 2. So 7 plus 5 is 2 mod 10. That's the modular addition. Let's do a modular multiplication. 7 times 5 mod 10. Look here, 7 times 5 is 35. And 35 mod 10 is 5. Because 35 divided by 10, well, that's 3 times 10 plus 5. So we say that 7 times 5 is 5 mod 10. Last example, to the power 5 operation. So 7 times 7 times 7 times 7 times 7 is quite a big number. But if we reduce this, we also say reduce sometimes for the modular operation, reduce it mod 10, then you simply obtain 7. This is actually quite odd. If you look at it, a number to the power 5 equals the same number mod 10. It can happen, and it certainly looks interesting. It actually will have a lot of interesting consequences in terms of properties which are explored in the number theory, and this is also used effectively in cryptography. So let me just briefly introduce something else which is useful when we are talking about modular arithmetic, which is the property of associativity. We say that an operation is associative if we can compute intermediate results in any order. So we're kind of thinking of brackets grouped around intermediate results, but we can actually do this in any order without affecting the final outcome. And this is something we're very much used to, but people don't normally talk about it. They take it for granted. You know very well that if you add 3 numbers, let's say 1, 3, and 4, then really it doesn't matter whether you add 1 plus 3 first, so that's 4 plus 4, or whether you do 3 plus 4 first, which is 7 plus 1. In any case, the output will be 8. That's fairly clear. This applies to multiplication as well and to exponentiation. So maybe it's not surprising that that's correct for modular arithmetic as well, but maybe it is. But anyway, it is true. And that's sometimes very useful because you can actually save a lot of work when you wanted to compute, let's say, a complicated modular exponentiation task such as 2 to the power 5 and the whole thing squared mod 30. So the frustrating thing is this number itself is quite big, but then if you reduce it mod 30, then it will definitely be quite small. And the question is, can we not perhaps do the modulo operation in the intermediate stages cleverly so that our results remain small and then it's easier to compute? And you can do this because of the property of associativity. Otherwise, it wouldn't be possible. But I can basically tell you, yes, feel free to do it. It will work. So let's see how we can compute this output here then. So if you actually write down carefully 2 to the power 5, and then you squeeze in the mod 30 first, before you square the whole thing and take the mod again, then you can see that here 2 to the power 5 is 32. And 32 mod 30 clearly is just 2, right? That's quite straightforward. So what you have here is effectively 2 to the power 2, so 4. And 4 mod 30 is clearly 4. So you have computed this output without any complicated number crunching in your head. On the other hand, if you did the brute force method and you actually computed the 2 to the power 5 squared, you come out with 1024. And then to reduce 1024 mod 30, you do, of course, you can do it, but you need to kind of think a little bit, and you will see that it's also 4. So we haven't made a mistake. But this would be the preferred way, and it's not only useful as a kind of aid for computing in your head, it's also actually used in theory, sometimes in proofs, and in particular the proof of the correctness for the RSA algorithm will require this sort of reasoning. So now as the mini exercise 3, can you exercise the modular arithmetic based on the sum of 5 and 7 mod 10? Can you compute 1 plus 1 mod 2? Can you compute 1 minus 1 mod 2? There's a product and there's a power. So one last useful concept to do with modular arithmetic are the modular arithmetic tables, particularly useful for small modulus values, and also just to maybe illustrate the nature of the operations in terms of some nice patterns. So what we do is we introduce these tables to simply illustrate the output of the modular arithmetic, let's say in terms of addition and multiplication. So here, maybe it's easiest just to look at those tables straight away as examples. We have the addition plus modulo 4, so the input can only be one of those 4 values, 0, 1, 2, or 3. So we put both inputs here in terms of the columns and the rows. So then what we do is any position, let's say here in row I and in column J, then what we do is we actually assign the sum of I plus J. Depends how you numerate it. Effectively, if you start counting maybe with row 0, you would say this is row 0, this is row 1, that's column 0, that's column 1. So if you want to know what's in here, that's the sum of 1, so row 1, and 1, so column 1. So 1 plus 1 is 2. That's quite straightforward. It's just the sum really of 1 and 1. But it gets interesting, let's say here, where you have 2 plus 2, mod 4 is 0. So if you do this for all those values, then you get an interesting pattern. And if you do it for the multiplication as well, you also get a pattern, but that's obviously different. What are the interesting things I mean here? First of all, you can see that the operations are commutative. It means that effectively there's a symmetry. There's some kind of symmetry axis here, and the 1 you can find it here, the 2 you can find it here. It's all sort of it's symmetric, which is obvious. We haven't really insisted on it earlier, but it's another property in the same way as associativity is a property. The commutative property means that you can exchange the order of the input and the output will be the same. And then there are other interesting things for the multiplication. So for example, look here. Apparently, if you take 3 times 3 mod 4, the output is 1. That is fairly unusual because for the multiplication, normally we would not expect 2 integers to be multiplied to turn into 1. normally you need fractions for that. Yeah, you would typically need 3 times 1/3 to give 1, because 1 is somehow, it's kind of a neutral element somehow with respect to the multiplication. So it's quite interesting that here we can somehow simulate this 3 and 1/3 multiplication by just doing a mod 4, 3 times 3. We'll come back to this later when we introduce the modular inverse. And then also another interesting fact is that you can multiply two numbers that are non-zero, 2 times 2, and you obtain 0. That is also highly unusual. If you don't have the modular arithmetic, just normal integers, you would never ever obtain 0 if you multiply two non-zero elements. So interesting new phenomena arise when you consider the modular arithmetic. So now, as another mini exercise, can you sketch a table similar to the previous ones for addition and multiplication, modulo 2, so the tables will be much smaller. And then can you already think about one more thing here using the booleans? So we haven't really introduced Boolean operations yet, actually, but you can maybe research this briefly on the internet. So can you somehow imagine if you use Boolean truth values instead of the numbers? So 0 would be false and 1 would be true. Whether you could make sense of those operations in terms of some operations on the truth values. So we will leave the integers and the integer arithmetic and modular arithmetic behind now, and we'll briefly study polynomials and see what we can do with polynomials in terms of arithmetic. And actually it turns out that it's in many ways very similar to the integers, which is perhaps surprising because polynomials look more complicated, but they seem to behave in some ways quite similar to integers, because we can obviously add them as well, we can subtract them, we can multiply them, and you will do this in a minute for the mini exercise. But this is all, things you have done at school when you combine the like terms, you combine the x's and the x squares. So that's all basically simple polynomial arithmetic. But then perhaps more surprising, you can also divide a polynomial by another polynomial f by g, and you obtain a remainder. You can actually use the degree here as a means of describing the properties of the remainder. So what you want to do is, if you have a given polynomial f and you would like to divide it by g, and we're assuming here that the degree of g is smaller than f, otherwise it's not going to work. Well, it will work, but it will give you a 0 remainder. Then basically write f as a product of another polynomial q times g. So you need to find q and r so that the degree of r is less than the degree of g. We will practice this in a little minute, and you might have done it at school. There is an algorithm to do this, and it's very interesting, and you could take this further by introducing, the idea of modulo operation based on a polynomial modulus, but we're not going to do this now for the scope of this lecture. So basically, just to summarize, try to get familiar with the polynomial arithmetic in terms of plus, minus, times, and perhaps division by remainder. And then there are two more things that are very useful and important when we think about cryptography, applications to cryptography: the evaluation of a polynomial and the task of interpolation. So very briefly, what is that? Evaluation of a polynomial at a given point x equals x0 is not difficult. So here, this is just again the idea to view your polynomial as a function. So if you see your polynomial f as a function f of x, then it's quite straightforward to replace x wherever it occurs in your polynomial with a value, let's say x0. So you do this substitution, obtain effectively an expression involving integers. So you just do simple integer arithmetic and you will obtain a number. and that is called the evaluation. And then there's another interesting question. Could it be possible to actually do a number of evaluations of a polynomial in different points, of course, so that you obtain a collection of points? Yeah, this is basically a point. It's an x value, x index I, and the corresponding f of xi value, which is effectively y index I. So you can think of a Cartesian coordinate system, but basically, am I able to collect some of these points so that I can actually reconstruct the original polynomial? That's very useful. And it turns out if you have a polynomial of degree d, then you would need d plus 1 such distinct points in order to reconstruct it. You can intuitively see why that's the case, let's say for a linear polynomial. A linear polynomial is nothing else than a straight line. So what is the degree of a linear polynomial? Linear meaning degree equals 1. It's just a straight line ax plus b, for example, if I use those variables. So a straight line is clearly uniquely determined if I have 2 points, because then I can connect them using a ruler. So that's just one unique way of doing it. So if the degree is 1 for the straight line, then I need 2 points, d plus 1, 1 plus 1. So that's obviously not a proof, but it just shows you that that seems to make sense, certainly for the case of a linear polynomial. In case of a parabola, which is a quadratic function, a polynomial of degree 2, we would need 3 distinct points to uniquely kind of determine the parabola that goes through the 3 points. You can practice now the polynomial arithmetic based on this mini exercise. So just compute the sum and the difference and the product of those two polynomials, x cubed minus 3x plus 1 and x minus 1. And then also try to divide f by g using the division with remainder algorithm. And finally, practice the evaluation and interpolation tasks based on this polynomial here. So evaluate the polynomial 3x squared minus 4x plus 5 at the points x equals 0, 1, and 2. And then another exercise, given the points 1, 1 and 2 minus 3, can you compute the straight line going through those 2 points? So that's a polynomial g of degree 1. And that's sort of basic linear algebra, solving a system of equations, but you can also do it by guessing. So there are different ways of doing this, and obviously if the polynomial is of a greater degree, if you have more points, this gets more and more complicated. There are several methods in order to do interpolation. We're not going to go into details so for the scope of this lecture. And now finally, I would like to talk about Boolean algebra a little bit and to kind of present typical operations on truth values based on what we call a truth table. Now, Boolean algebra was invented by the English mathematician George Boole, and his idea was to encode the kind of typical things you do when you reason logically in terms of using then operations. And what turns out is that if you want to manipulate truth values such as true and false, these are really the only ones we consider certainly for the classic Boolean algebra, then the operations that you need are the negation and the conjunction and the disjunction. That sounds all a bit complicated, but really, if you look at this table, you will see that this is the not operator. So it basically just inverts the input. If x is false, then not x is true. If x is true, then not x is false. So 0 turns to 1. And then you have the AND operator, x and y. And x and y is only 1 if both variables are true. So true and true is true, anything else is false. And you can clearly see the relation to the real world if you make statements such as a student will pass his degree if he passes all the modules and also passes the final project module. So X is passing all the modules, Y is passing the final project. So if and only if both are passed, then the degree would be passed. That's quite straightforward. The example of the OR function here is also quite straightforward. You can see this in real-world examples. Let's say if I say I'm happy if either the weather is nice or if I'm greeted in a friendly manner on my way to work. So X would be the weather, Y would be being greeted. So then clearly if the weather is nice, X equals 1, then I'm happy. If I am greeted, then I'm happy too. If both happens, then I'm certainly still happy, so 1. And only if none of those two things have happened, then I'm not happy. So that's the OR function. And it turns out that you could think of obviously other combinations with other outputs here in terms of the input, and some of them might make sense more or less straightforwardly, but they all have some kind of meaning, but they can actually all be derived based on those 3 elementary operations. So really we don't actually have to consider anything else, but still in day-to-day life there are interesting things we would say and sort of imply, and hence they still deserve the introduction of those 3 additional operations. So I will very briefly go through this, and then that's basically enough for the purposes of the lecture. So let's start with the exclusive OR operator, or XOR operator, that's used quite a lot in computer science. So basically the exclusive OR is very similar to the normal OR, but it is not actually allowing both inputs to be 1. So when we in day-to-day life say OR, we typically mean this OR, the kind of inclusive OR. But then sometimes it might be useful to exclude it, in which case you get these values here. So the exclusive OR will only return a true if there's exactly one input that is true and the other one is false. Then the next operator is the inclusion. Sorry, not inclusion, the implication, of course. So X implies Y. And this is probably best understood using an example. So if, let's say, look here, X means it is raining and Y means the ground is wet, then the X implies Y values here clearly show you a situation where, let's say, let's start perhaps with here. If it's not raining, then could it be that the ground is not wet? So if it's not raining, then certainly it's true that the ground could be dry. On the other hand, if it's not raining, could it also be true that the ground is still wet? Yes, it could. Look here, true. Because the ground could be wet for other reasons. Someone might have hosed it down with a hose pipe. Could it be that it is raining and the ground is dry? So here we say no. So we're assuming there's obviously no protective roof or anything. So really, if it's raining, the ground will inevitably be dry. And then if it is raining and the ground is wet, that's obviously exactly what we observe. So here, that's true as well. And the last operator is the equivalence. And that basically just means that x and y have the same value. So here this is true if both x and y are false, or both x and y are true, and if they're different, then it's false. So you could spend a lot of time thinking about this and doing some exercises with logical statements and translating them into expressions in Boolean algebra, but that's not really the purpose of this lecture. I will just finish by saying that if you now think again about binary numbers and this idea that the logical operators here could then also be applied to binary numbers if you look at the different digits, so bitwise, then you start implementing operations on binary numbers, and that will effectively lead to implementing logical operations in a computer. And hence the mini exercise, can you try to compute the exclusive OR operator for those two inputs? And if the inputs do not have the same number of binary digits, you need to add leading zeros to the left of this number here. Can you also compute an example with the OR operator and an implication? So let me just summarize now this part of the lecture for the mathematical operations. We have introduced modular arithmetic. We have looked at integer arithmetic first of all. We have then defined the modulo function, and we have seen that if you kind of combine both, then you achieve something quite interesting, which is called modular arithmetic. We've studied some basic properties. We've seen a modular arithmetic table, just with the aim of understanding more in detail how to do this and what might be important about it. We have then done some basic polynomial arithmetic, including the evaluation and interpolation. And finally, I have introduced some principles of Boolean algebra and the basic logical operators as illustrated by a truth table. And what we would like to do now is to go further and actually create something more complicated based on several steps and sequences of basic operations, so effectively leading to an algorithm. So we're interested in mathematical algorithms, and really we're primarily doing this with the integers, and in fact with using modular operations. So we're interested in computing what we call the GCD, the greatest common divisor, and also the modular inverse. So now let's talk about mathematical algorithms, and we will be interested in two computational tasks. The first one will be to compute what we call the greatest common divisor. So I will first explain what that actually is, the GCD we call it as well, and then present basically two ways of doing it. And then we will introduce the modular inverse and explain how to extend effectively the algorithm from the first section to then compute that modular inverse. So you can see the learning objectives then. First of all, to understand the concept of the GCD, the greatest common divisor, and then to be familiar with what we call the Euclidean algorithm. This is a very old algorithm, and it can be used to compute the GCD. We'll do some detailed explanations and examples of that algorithm. And then we will understand the definition of the modular inverse. And then you need to be able to use an extended version of the Euclidean algorithm in order to compute the modular inverse. So then let us introduce the definition of the greatest common divisor. So if you have two integers, a and b, then the GCD of a and b is simply the greatest integer that you can find so that it divides both numbers. And the easiest thing to do in order to understand it better is to probably look at an example. So here, look at two numbers, 28 and 24. So the GCD of 28 and 24 is 4. Why is that? Well, first of all, clearly 4 is a factor of 28, and 4 is also a factor of 24. But then any other number greater than 4 will not be a factor of both numbers. As you can test, 5 wouldn't work, 6 is a factor of 24 but not of 28, 7 a factor of 28 but not of 24, and you continue until you quite easily reach a number that's greater than both numbers, then it can't work anymore. So clearly there's no other number greater than 4 that divides 28 and 24, so the GCD must be 4. So how could we then compute this in general if we have other numbers, maybe bigger numbers, where it's not so easy to do a trial and error? So you probably have done this at school. I mean, it is something typically school children do. However, they're not always kind of clear about the underlying algorithm. And I've given you a formal description of the way you typically do it at school based on the prime factor decomposition. So really, if you have actually managed to decompose the two numbers a and b into their prime factors, then the task is quite easy. Of course, the problem will be that for bigger numbers, it's very difficult to find those prime factors. But nevertheless, let's assume you have actually decomposed the number a as a product of p1 times to the power alpha 1 times the p2 power alpha 2 up to the nth factor pn to the power alpha n. And you have also obtained a decomposition of b using, and that's quite important to notice here, the same prime numbers. And actually, when I say prime numbers, they're not necessarily prime numbers, they can also be 1, because basically what you need to do is you need to make sure that these are the same numbers. So p1 obviously here with a certain multiplicity alpha 1 and beta 1 all the way to pn to the power alpha n and pn to the power beta n. So it could be that some of those exponents are actually 0 if by chance that a number p index I that's in that composition doesn't actually occur in the other decomposition. Then you just say beta index I equals 0. So basically try to figure out the exponents alpha I and beta I. And once you've got that, then it's quite straightforward, because then the GCD is simply the product of the powers of the PI, but you take the minimum of the exponents between the minimum of the alpha I and the beta I. So that's the idea behind it, and it looks more complicated than it actually is. And you will have an opportunity to try this in the mini exercise coming up, and then it should be clear, and you will rediscover that that's really how you do it naively, if you remember how you were taught at school. So basically, just to summarize this again, we can compute the GCD quite easily, provided we actually have a decomposition, a factorization into powers of primes, because then we can basically just take the minimum power that is jointly, occurring in those factorizations. So another definition, we say that two numbers a and b are coprime if the GCD happens to be 1. And that's quite an important property which is used a lot. So it's worth giving it its own notion. That's why people call it coprime. So now I will introduce the Euclidean algorithm, which is basically a second way of computing the GCD, and you can use it for other things as well. So it is based on a recursive way of actually computing the GCD, and I'm not going to prove it now, but the GCD of two numbers a and b is actually the same as the GCD of b. So you take the second argument, it becomes the first argument, and then as a second argument you actually reduce the number a modulo b. So you take the remainder of dividing a by b, which is an interesting formula. So if you kind of think about this, then what it means is that the input is actually reduced in size. So eventually you'll end up in a situation where the second argument becomes 0, and then you can clearly see that the GCD of a and 0 is a, so you're done, which we call the base case sometimes when you have a recursive definition. So if that troubles you, don't worry, because we don't really need to understand the recursiveness of this definition. We just need to be able to actually run the algorithm, and the best way is probably to do this using an example. So just be very careful when you do this and always stick to my notation, because otherwise you get stuck with the extended version of the Euclidean algorithm in the second part. So let's look at the example of computing the GCD of 80 and 45. So what you're going to do is, first of all, it's going to be a number of steps. Each step I write in one row. So let's start with the first row. So you're going to divide 80 by 45. So you take, and by the way, make sure you put them in an order so that the first argument is actually greater than the second argument, so you can divide. So here 80 divided by 45 is clearly 1. And then you need to work out the modulo. You need to work out the remainder. And the best way to do this is to say, all right, then 80 minus 1 times 45. So the 1 is obviously this result here. So 80 minus 1 times 45 is 35. So you're done with the first row, the first step. Now look carefully in the second step. What you're going to do is, and that's basically this transition from, from this left-hand side of the recursive definition to the right-hand side, you're going to shift the second input to become the first argument. So the 45 becomes your first input. And then what you're going to use as the new second input is the result from the previous step. So the 35 becomes the second argument. And then you start from the beginning again. So you're going to divide those two numbers, 45 divided by 35. So here the quotient happens to be 1 again. And now the remainder, the leftover, is 45 minus 1, because of the 1, times 35 is 10. So you're going to now go to the third step, where you shift the second argument to become the first, 35. And you copy through the result, the leftover, 10 to become the second argument, and you start all over again by dividing 35 by 10, which is 3, and the leftover now is 5. If you do this once more, you're going to shift the 10 divided by 5, which is 2, and now the leftover, the remainder, happens to be 0. As soon as you reach a 0 here, you will be done. The good news is there will always be a 0. If you don't get a 0, you must have made a mistake somewhere. So as soon as we have the 0, the algorithm terminates. And now what you can show is that the GCD, the desired result for the GCD, is the penultimate leftover here, the last non-zero remainder. So in our case, the number 5. And if you think about it, then writing down these different steps is nothing else than actually unrolling the recursive definition. So the GCD of 80 and 45 is, according to the recursive identity up here, the same as the GCD of 45 and 80 modulo 45, which we have computed to be 35. So actually, if you are in the second step, then what you know is that the outcome from the second step will be the same in terms of the GCD, will be the same as in the first one. So it's like an invariant. And as you make progress in those different steps, eventually you are in a situation where you have, if you went one step further, you would have 5 and 0, and we clearly know that the GCD of 5 and 0 is 5, and then you're done. And that's the reason why you can stop when you have the 0, and then it's that number here. So that's all that's behind it. But as I said, don't worry, as long as you practice doing the algorithm with exactly this kind of syntax, so notation, then it should be quite straightforward. The advantage of this algorithm is it might look more complicated than the school method, but actually it will be much faster, especially as soon as the numbers get bigger. It will be surprisingly quick in terms of numbers of steps you have to do, even if you're working on, 4-digit numbers. And if you implement it in a computer, it will be very efficient even for really big numbers. Whereas you wouldn't be able to do the factorization method from the previous slide. So that's really the main reason why we want to use the Euclidean algorithm to compute the GCD. So now you can do the mini exercise 8, where I want you to compute the GCD of 75 and 28. And you're going to compare and contrast, first of all, the school method using prime factor decomposition, where you're going to write 75 and 28 respectively as a product of powers of numbers, which are either prime numbers. Well, there will be prime numbers, but you just need to make sure you actually have the same prime numbers occurring, and you choose your exponents accordingly, and then you can work out the GCD by taking the minima of the exponents as explained. But then the second method would be to run the Euclidean algorithm on this input, and then hopefully you should get the same. So that's a good exercise. Second exercise would be to still practice the GCD, and I should say Euclidean algorithm here, with input 799 and 987, which looks awkward. These are awkward numbers, but if you use the Euclidean algorithm, it should be relatively quick. And as a bonus exercise, you could try the optional task to find integers x and y, so that this linear combination with the input number 799 and 987, so times x and times y, equals the GCD that you have just computed. It's non-trivial to kind of hope that that would be the case, that you actually get these numbers, but you can show that they will always exist and that they're actually unique. And if you look carefully when you do the GCD, you can, the algorithm, the Euclidean algorithm, you can actually see quite easily how to, well, it's not that easy, but you can fabricate those numbers. So we'll come back to that later when we practice the extended Euclidean algorithm. So now we come to the next definition that we require before we can proceed with the algorithms, the definition of the modular inverse. So let a and n be two integers, and what we're going to say is that the inverse of our number a with respect to n, or modulo n, is another integer with the property that if I multiply the first number with that integer x, that then if I take that product modulo n, it is actually congruent 1. So they are kind of each other's inverses, because what you kind of think is for rational numbers, you know well that let's say the number 2, well, the inverse of the number 2 over the rational numbers would be 1/2, wouldn't it? So 2 times 1/2 equals 1. Now with the modular arithmetic, and that's what we're doing here, we're doing modular arithmetic, you're not necessarily really, well, you don't necessarily have a corresponding number so that you actually find this inverse, but if it does exist, then you would call it an inverse, wouldn't you? So it is literally just mimicking this idea of having a fraction, effectively. And then also clearly, if x is the inverse of a mod n, then a will be the inverse of x mod n. And because we're thinking of the fractions, and 1/2 is nothing else than 2 to the power minus 1 by definition, we also use that notation here in the world of the integer modular arithmetic. So we also write a to the power minus 1. Although it doesn't really make sense normally to say 1 over a, but we are kind of thinking just of the outcome of the property that the product of a and this other number, which we call a to the minus 1, that product would then still be 1 or congruent 1 modulo n. Okay, so I've talked a lot now. It's probably better to look at some examples. So if I gave you the number a equals 3 and the number n equals 20, then you could wonder what would be the inverse of a mod 20, the inverse of 3 mod 20. And then if you play around a little bit, you do try and error. And if you end up testing the number x equals 7, you will realize 3, so a3, remember, 3 times 7 is 21. Oh, hang on, so 1 mod 20 is clearly 1, which is exactly what we wanted based on the definition of the modular inverse. So clearly 7 is the modular inverse of 3 mod 20. And then of course the other way around, the modular inverse of 7 mod 20 would be 3. So for small numbers, it's fairly straightforward just to do trial and error, and you can work out the modular inverse. Sometimes, though, it doesn't exist. It doesn't always exist, and in fact, we can't exactly state the conditions under which the inverse will exist, if and only if the numbers a and n are co-prime. So if the GCD of a and n is 1, then I can actually find such an inverse, and it will be unique. We will later see that this is very important in the cryptography for computing the RSA keys. So very important. There's only one actually of many other important applications really of this fact, and many theorems use that fact. So now we're asking ourselves how we can compute the modular inverse other than just try and error. And of course, if you had a multiplication table, as you've seen previously in this lecture, if you have, let's say, the multiplication table for the modulo 20, obviously that would be already quite a big table, then it would be enough to find the number 1 somewhere in the middle of inside the table and go along the rows and columns and make it so that you actually get the 3 and the 7 matching up. So you could easily see the inverse. But what if the numbers are bigger? Then I would recommend to use the extended version of the Euclidean algorithm, which actually computes something which is kind of linked to the mini exercise, the optional part of the mini exercise from just earlier, which is to do with the linear combination of the input A and B. So that's all a little bit tricky and theoretical, and if it doesn't really mean much to you, then just skip over this. And the important thing really will just be to be able to run on an example the extended version of the Euclidean algorithm based on the steps, the scheme that I will show you on the next slide. But if you are interested in the theory as well and want to understand a little bit more why it does compute the modular inverse, then just look at this fact here. So the fact is that the extended Euclidean algorithm, or EEA as people sometimes say, does the following based on an input, A and B. It will do actually two things. So first of all, it will actually run the normal Euclidean algorithm anyway, so you already obtain the GCD of A and B, as you have seen. But then furthermore, it will go beyond and it will compute those numbers if they exist. Now they do exist, apologies, they will always exist, U and V, so that this linear combination equals the GCD. So that's the general kind of output of the extended Euclidean algorithm, but what we are interested in is a situation whereby the numbers A and B are co-prime. And then I did say just now that then you can show that the modular inverse exists if and only if that's the case. So now what I'm claiming is that actually then the number u that is computed here in the extended Euclidean algorithm is exactly the desired modular inverse of A mod B. And why is that the case? Well, it's actually quite easy to see, because if you look at this equation here, and you imagine that the GCD is indeed 1, because we have just assumed that A and B are coprime, so then actually this equation here is the same as UA. So look here, UA equals, so I'm just bringing this thing here over this term to the other side, and the GCD is 1, so really all we get is we get UA equals 1 minus VB. So if you look at this equation carefully and take it modulo B, then you realize that actually VB will be 0 mod B. So all that's left is UA congruent because of the modulo 1 mod B. But that's exactly the definition of the modular inverse. So we have just seen that now, based on the input A, we have computed a number U, so that the product is congruent 1 mod B. So then U must be the modular inverse of A with respect to B. So that's exactly what the extended Euclidean algorithm can do for us in this scenario here, where we want to compute the modular inverse. So if we look at the example from the previous slide again, then we had A equals 3 and B equals 20. So if we launch the extended Euclidean algorithm, it will compute numbers U equals 7 and V equals 1, such that, so if you compare this now, so it's the linear combination, so 7 times first number minus V, which is 1. So that should be, actually, apologies, that should be minus 1 here. So 21 minus 1 times 20 is 21, minus 20 is 1. So indeed, we have computed or expressed the GCD, which is 1, as this sort of linear combination. And then we realize that this number here, the number U, 7, is indeed the modular inverse, as you have seen before. And of course, that seems not clear how you can actually compute then those numbers U and V, but that's exactly what I'm going to present now in the scheme for the extended Euclidean algorithm. And then you are equipped with a method that helps you to compute the modular inverse. So look at this example then. The task would be to compute the modular inverse of 29 modulo 41. So we're going to do as a step 1 the Euclidean algorithm, as we have introduced already. So let's just go through this again carefully. So you're going to order your input by having the bigger number first, 41, and then what you need to do is you need to divide by 29. The quotient is 1, and the remainder of that division turns out to be 12. So in the next step, remember, you're going to make the second argument become the first and copy through the leftover from the previous step. So 29 divided by 12 is 2, and the difference between 29 and 24 is 5, so leftover is 5. Do one more step, shift the 12, copy 5. The quotient is 2, leftover is 2 as well. So we still don't really know whether we're done or not, because we need to find a 0. But actually, if you do one more step, so copy, shift 5, copy 2, then your remainder will be 1, and at this stage you can actually stop. Why is that the case? It is the case because your next step will bound to yield 0 as the remainder, because in the next step, imagine to take the 2 and divide it by the remainders by 1. So 2 divided by 1 will be an exact division. So the remainder will be 0. So you will have your 0 at the end. So you will know that you're done. And then the previous non-zero left over will be the GCD. But that's 1. So you know that anyway. So whenever you get a 1, then you know that you're actually done. Okay, so what we've done now is we have actually asserted that the GCD is 1. So 29 and 41 are coprime, and that's the essential precondition for the existence of the modular inverse. So that's good news, basically. So now we can continue, and how does it work? So basically, the step 2 is very much oriented by the step 1. If you had 4 rows in the step 1, you will also have 4 rows in the step 2. Now, basically, the beginning is a little bit tricky because you have to remember it. You have to remember that you're always going to take the number 0 and the number 1. And then what you also need to do is, in each step, you're going to basically perform an operation, like a linear combination, and the factor here in the middle is always taken from the first step in the corresponding row. So this -1 here is the reason why you've got a -1 here. So 0 minus 1 times 1 is 0 minus 1, which is -1. So we've done the first row now for the step 2. And now you do a very similar operation, and you just need to be very careful not to get muddled up, and also with the minus signs, which creep in quite a lot here. You need to use brackets, not to perform an error in your calculation, a sign error. So how do we go from the first row to the second row? Well, we do a similar thing in terms of shifting the second number to become the first number, similar as in the step 1 of the algorithm. And then you will do also very similar. You will copy the result from here to become the new second argument. And as I said, if that happens to be a negative number, make sure you put brackets around it, just in case. So now the last thing you need to know is what is the operation I'm supposed to perform actually. This factor here, well, you're going to copy the -2 from the step 1, the second row. Yeah, so we've got now all those input numbers, so we can compute the results. So 1 minus 2 times -1, so -2 times -1 is +2. So it's actually 1 plus 2, which is 3. Okay, so we're halfway through. Let's do one more row. So once again, we copy the -1, become -1 here, the first argument. And then the second argument will be the remainder here. Well, not remainder, the output basically, so 3. And I'm going to copy the -2 from here. So -1 minus 2 times 3 is -1 minus 6, which is -7. One more row, copy the 3 over to become the first input, and take the -7 to become the second argument, and copy the -2 from here to -2, which gives 3 -2 times -7. -2 times -7 is actually plus 14. So we get 3 plus 14 is 17. So finally, we're done. Because actually what I'm claiming is, and we haven't really proven it, but you just have to believe me now, this number here is the output. So the modular inverse of 29 mod 41 is 17. And as a little exercise, I would ask you to verify this based on the definition of the modular inverse. You might want to use a pocket calculator, and then you will see that this is indeed the correct result. So to summarize, the extended Euclidean algorithm uses a second step, which is closely oriented by the first step, and it will copy through the operation from the first step, and it'll do a very similar sort of shift pattern for the input numbers, and then in this way you will finally obtain the modular inverse of the original input. So as an exercise, first of all, it would be very important to practice this. Practice this as much as you can. You can choose your own numbers, but try it first on the input 28 and 75. So compute the modular inverse of 28 mod 75. So you will have to run the extended Euclidean algorithm. And the first step, of course, will be to compute the GCD using the Euclidean algorithm. So don't forget to put the parameters, the input parameters, into the right order. And then once you've done that, then we can have some other very interesting and useful applications of the modular inverse. So solving linear equations, modulo an integer, can basically be done provided you can compute the modular inverse. So you could try to solve those linear equations, 8x congruent 1 mod 13, and 6x congruent 11 mod 29, and also 8x congruent 7 mod 11, based on this idea of computing the modular inverse first. And of course, you need to carefully think which number are you actually going to need the modular inverse of. So that would be the second mini exercise. And that finishes our section on the mathematical algorithms. Now, the last section of this lecture is actually about number theory, computational number theory. And number theory is a very specialized and very difficult area of mathematics. For a long time, people used to refer to it as the queen of mathematics. And it's only thanks to modern cryptography that we have actually found an application area, a serious and real-world application area for the number theory. Now, we're not going to cover at all a lot on it because it is very, very difficult, but just the very basics, and that will be enough for the scope of this lecture. So let's start with the learning objectives. So first of all, to understand the importance of number theory and computational number theory in particular for cryptography and for the RSA algorithm in particular. Then to understand the definition of what a prime number is, and to appreciate the difference in terms of computational effort and efficiency of prime factorization and primality testing. Furthermore, to comprehend the definition of Euler's function, which is a very important and useful definition, quite often used in theory, in number theory. And finally, to be familiar with Fermat's little theorem and Euler's theorem and their use, the various uses for cryptography. So what is number theory? Number theory basically studies properties of very simple mathematical objects, and we've seen lots of mathematical objects, of course, in this lecture, and we did start with the integers. So really it's all about understanding more about integers, and it was introduced in the 17th century by very famous mathematicians. You must have perhaps heard of people like Fermat, Gauss and Euler. And Gauss, who is perhaps the most famous one of those, once said that in the same way as mathematics is the queen of the sciences, that the number theory is the queen of mathematics. So to him, it seemed that the results that number theory states are sometimes so difficult to prove actually, and yet so beautiful, and also perhaps detached from any reality, because people didn't really have any application area for the number theory, that he thought it's like a queen of mathematics. So nowadays people know that it's actually very difficult to prove even very simple mathematical properties. And as I just said, for a long time we didn't really have any applications of number theory, but nowadays the invention of public key cryptography really made it clear that there is one, there's a really important one. So in particular, the RSA algorithm was the first time when people made really good use of some very old number theoretical results, and that's in use nowadays every second. Every second someone out there is going to encrypt information using the RSA algorithm, and that's when the number theory kicks in. So now let's look at prime numbers, which are a very important ingredient in the number theory. So just by definition, a prime number is simply any integer, and we're going to assume an integer greater than 1, otherwise it's trivial. And what we define is that this number is a prime number if and only it is divisible by itself and 1. So in other words, it doesn't have any non-trivial factors. So for example, you can see this list 2, 3, 5, 7. If you take any of those numbers, the number 1997 as well, then you would find that you can't actually find any proper divisor. So they only have 1 and itself as a divisor. So clearly these are all prime numbers. And it's quite difficult really to know just by looking at a number whether it is prime or not. In fact, you can't basically. You have to run a test. It's quite easy to see that there is an infinite number of prime numbers. The list goes on forever. That's a very clever proof, because basically what you say is assume that you did find indeed the biggest prime number. Then actually what you can define is you could define the product of all prime numbers, including that biggest one plus 1, and you can show that that's another prime number. So you would construct another prime number. So the list is indeed infinite. Now, in terms of wanting to decide whether a given number is prime or not, it turns out that computers can actually decide this relatively efficiently. It's what we call a non-deterministic algorithm. So it's kind of a randomized algorithm. It doesn't always run with the same speed and might need a certain number of iterations, which is difficult to predict, but it will give the answer eventually. And so it's quite efficient really to decide whether a given number is a prime number. On the other hand, the related task of taking an integer which is not a prime number and factorize it into a product of prime numbers is actually computationally very difficult. And we will see that the security nowadays that we need is relying on the difficulty of that problem, of the factorization of big numbers. So just look at the example. So for example, 10 can be written as a product of the prime number 2 and 5. 12 can be written as 2 times 2 times 3. So basically any non-zero integer, of course unless it is a prime number already, can be written as a product of prime numbers. So as a mini exercise, you're going to decompose the following numbers into their prime factors: 33, 45, 1001, and 2020. 2020. This is today's year. So now we will introduce Euler's function, quite often written as phi of n. Phi of n, which plays a very important role in computational number theory, and it is often used to kind of make more complicated things happen, to express complex statements and theorems that relate to integers, but then you can use the function phi as a part of the statement, and it's also very useful for proofs. So later in a different lecture, you will see that you can use it to prove that the RSA algorithm actually works. So how do we define it? For any integer greater than 1, phi of n is basically those integers in the set of sequences from 1 to n minus 1 that are co-prime to n. So we're counting all smaller numbers. We're counting those that are actually having a GCD 1 with the given number. It's a kind of counting function. So how would I write this formally? Look here, the formal definition, and that's kind of looking complicated, but really what it means is those bars to the left and the right, that just means the size of a set. So really what we're interested in is the set. The set is here with the curly numbers from here to here. That set is nothing else than a set, well, a subset of the set of numbers from 1 to n minus 1. So we're just doing exactly what I have written informally here. So we take all numbers, all integers that are smaller than n, and we look at each of them. So that's our k. And if that number k has a GCD with k comma n equals 1, so if k is co-prime to n, only then we include it in this overall set. Yeah, and then if we take the size of that set, then obviously we have counted the number of such integers that satisfy this co-prime condition. And that is by definition the output of the Euler function, which seems, it seems kind of weird. It's not clear why this would be useful, but it just turns out that that's a really important thing to know about a given number, which is, how many smaller numbers are actually co-prime to that number. That's just the way it is. Obviously an amazing discovery by Euler many, many years ago. And you can practice this now in this mini exercise here. So try to compute phi of 15. So just as a tip, based on the previous definition, what you need to do is you need to successively look at all the integers from 1 to 14, and for each of them decide whether the GCD of that number and 15 is 1. And if it is 1, you include it in your list. So basically you count it. So the number of those occurrences, that will be exactly the output of the function phi. So we now come to the last theory slide, presenting Fermat's little theorem and Euler's theorem. So I say little theorem because Fermat's theorem, which is kind of the big theorem, is something completely different. And that's the famous theorem that people have written about quite a lot, because for a long time no one really knew the proof, and Fermat had claimed he had found a really short proof, but then only kind of very much later people were able to actually prove it. But it actually required computers initially, and it was very complicated. But anyway, this is all about Fermat's little theorem and an extension, a generalization of it, which is Euler's theorem. And so basically just roughly what they actually say and why they might be useful for the cryptography. Yeah, so these two related theorems are all about taking any number a and repeatedly raising it to the power 2, 3, 4, etc. So multiplying it with each other, and then wondering what the result might be when you're using modular arithmetic. So you're going to take the output modulo p. So here Fermat's little theorem is all about p being a prime number. So what it says is that if p is a prime number, and also, and that's quite important, a is not a multiple of p. So let's just assume a is actually kind of a random number, but it must not be a multiple of p. In this case, which is kind of the generic case, what happens is if you take a and multiply it with itself, p minus 1 factors, so a to the power p minus 1, and take that result, modulo p, then you actually get 1, which is kind of a surprising output, isn't it? It seems strange, but if you obviously look into it more in detail, you will understand that it really makes sense, but that's not important now. All that matters is indeed if p is a prime number, then that condition is satisfied, and then equally if that condition wasn't satisfied for any number p, then you could work out that p must not be a prime number. And that's exactly how a very reasonably efficient primality testing algorithm works for the cryptography, which is called the Miller-Rabin test. So I'm not going to go into details here. And there are also some algorithms trying to factorize integers, which are using Fermat's little theorem. So these are roughly the application areas for the cryptography. But basically, just remember, that's basically how it works. That's what it says. And then the extension to Euler's theorem, the only difference really is that we're wondering what's going on if P is not actually, we're not writing P now, we write N, if N is any number. And then basically you get a similar statement here. Rather than the P minus 1, you now will have the Euler function, so a to the power of phi of n. And then the additional condition is that the GCD of a and n needs to be 1. And that's what we're going to use later when we're going to look at the RSA algorithm and the choice of the public and private key. Then you can show that actually it's thanks to this theorem here that you can prove, how that you can actually construct such keys which make the RSA algorithm work. Okay, so a last mini exercise to practice this. So basically use the number n equals 15 and a equals 2 to verify Euler's theorem. So what you need to do is you need to go and check simply this condition. Everything is given. A and n are given. So you need to obviously compute phi of n, but you might be able to use one of the previous exercises for that. So that's the first part of the exercise. Second part, can you somehow understand further how Euler's and Fermat's theorem are actually related? So in other words, if you wanted to kind of have Fermat's little theorem effectively as a specialization of Euler's theorem, then all you need to do is assume that n here is actually prime. So let's n be p, and then you will actually see that you obtain Fermat's little theorem. And lastly, and that's a little bit more complicated, can you show this condition here, this property, so a to the power p minus 1 times q minus 1 is congruent to 1 mod p times q, and it's actually not too difficult if I allow you to use Euler's theorem. So you are allowed to use this thing here. And also the fact that the Euler function phi is actually multiplicative. So if you have phi of n times m, then that's the same as phi of n times phi of m. You do not need to prove that. You can assume that. So let me finish by summarizing the basic number theory part of this lecture. So I hope that by now you understand the importance of the number theory for cryptography. You get a better feeling for the kind of things we want to do. As you have seen, there is modular arithmetic involved, and that's going to be one of the key ingredients for building and constructing keys for the RSA public key encryption algorithm. Furthermore, to understand what prime numbers are, and you've seen the difference between wanting to factorize them, which is difficult, and testing whether they are a prime number, which is easier on the computer. I've explained the definition of the Euler's function. We've done a small calculation with it. And then I have finished by introducing Fermat's little theorem and also its generalization of Euler's theorem. And we have briefly discussed their use for cryptography. This finishes this lecture, so many thanks for watching and I hope it's been helpful.